we're going to discuss the valence bond theory. Why did we need it and how exactly does it work? So even though we have a Lewis model which works on the octet rule and a VSEPR theory which can give the shape of almost every molecule, there are limitations to both. Such as the Lewis model cannot give the structure of a molecule. It can definitely show the bonds between the atoms. It cannot, however, explain the process of bond formation. Additionally, it cannot differentiate between the bond energies of hydrogen and fluorine molecule, both of which are very similar. Except that fluorine has additional lone pairs. On the other hand, the VSEPR theory can definitely tell the geometries of various molecules. It cannot, however, explain the reason behind these geometries. Therefore, in 1927, valence bond theory was given by Pauling and others to do away with these limitations. Let's find out how it works in a hydrogen molecule from two hydrogen atoms. When the two atoms of hydrogen approach each other, their nuclei attract their electron as well as the electrons of one another. Additionally, the two nuclei and the two electrons repel each other respectively. However, as the atoms come closer, the attractive forces are more than the repulsive forces, and hence the potential energy decreases. The point at which the potential energy becomes minimum is when the atoms are said to be bonded. At this point, the distance of separation between the atoms is called the bond length, and the potential energy at this point is known as the bond dissociation energy. Therefore, as you can see, the bond length of a hydrogen molecule is 74 picometers and its bond energy is 435.8 kilojoule per mole. At this point, the two s orbitals of the two hydrogen atoms overlap with each other to form a hydrogen molecule. Let's take another example of a methane molecule. The electronic configuration of carbon is 1s2, 2s2 and 2p2. In a methane molecule, 4 atoms of hydrogen form 4 single bonds with the carbon atom by sharing 1 electron each. However, as we can see, the 2s orbital is completely filled with 2 electrons and one of the 2p orbitals is empty. So how are the bonds formed? Also, the shape of a methane molecule according to VSEPR theory is exactly tetrahedral. However, as we can see, all of these orbitals have different shapes and different orientations. So how was this shape attained? Let's find out. So when the 4 atoms of hydrogen approach the carbon atom, one of the electrons from the filled 2s orbital is excited to the empty 2p orbital. These 4 orbitals, now of equivalent energy, then hybridize to form 4 identical sp3 hybrid orbitals. They arrange themselves in space to minimize repulsion and maximize stability and hence attain a tetrahedral configuration. It is with these configurations that the s orbitals of hydrogen atoms overlap to form a tetrahedral methane molecule. Let's take another example of tetracyanonickelate ion, that is NiCN4 2-. The oxidation state of nickel in this ion is +2 and hence its valence electronic configuration looks like this. It has 8 electrons in its 3d orbital and 4s and 4p orbitals are completely empty. However, in the presence of a highly negative cyanide ion, the 2 unpaired electrons in the 3d orbitals pair up, thus vacating one of the 3d orbitals. This 3d orbital along with 4s and 4p orbitals hybridize to form a dsp2 hybrid orbital. This along with the empty 4p orbital form a square planar structure. It is with this square planar configuration that the filled p orbitals of carbon atoms in the cyanide ion form coordinate bonds, and thus we get a square planar tetracyanonickelate ion. Therefore, as we can see, the valence bond theory not only completely explains the bond formation process, it can also give the accurate values of bond length and bond energies. It can also explain the magnetic properties of ions and molecules.